Okay, thank you all for coming to this fourth day of the workshop. So the first speaker of today will be Fearnhead from Lancaster, and he will talk about stochastic gradient PDMPs.
Okay, so thank you, and thank you to the organisers for the opportunity to speak today. This is joint work with a number of people, including Gareth, who I believe is running at the back of the audience. And it's a more methodological talk, and it's about using sort of PDMPs for Monte Carlo sampling. And the sort of basic idea is around the fact that these PDMPs have sort of nice properties in theory, but are very difficult to implement in practice. And therefore, to overcome that, one approach is to, rather than simulate the PDMPs exactly, is to simulate an approximation to them. We'll talk about one specific approach we've taken for that. And I should say that the original idea for sort of simulating sort of approximations to PDMPs actually comes from earlier work by Andrea, Joris, and others, and they actually have a very nice paper studying this, a lot of the sort of theory for this idea, some of which we use. So to start off with a bit of background on sort of PDMP samplers and what we're trying to do. So we're interested in sampling from some density pi of theta, and we're going to do that by simulating a sort of PDMP that has pi of theta as its sort of as a theta component of its stationary distribution. And there's a number of different sort of PDMP samplers that have been suggested, and what I'm going to talk about would apply sort of generally to any of them. But for this talk, I'm just going to focus on one of them called the bouncy particle sampler, just for sort of concreteness. And as common with any of these sort of PDMP samplers, the bouncy particle sampler works on a sort of augmented state space where your state space has both sort of a theta component and a sort of V component. And these are both going to be of the same dimension. And one way of sort of thinking about it is that you can think of theta as being a sort of position and V being a velocity. And then the dynamics of the bouncy particle sampler are just given by the sort of 3 bullet points on the screen. So the bouncy particle sampler is a piecewise deterministic Markov process, which means that it evolves in a deterministic manner in between some random events. And the deterministic sort of dynamics that it has is very simple. It's just a sort of constant velocity dynamics. Okay, so between the events, the velocity stays constant, and the position theta just evolves as you would expect given that velocity. Okay. You then have events which occur at some rate which depends on the current state of the process. So sort of given by this expression here. And the interpretation is that sort of V transpose grad log pi is just measuring how log pi is changing as we're sort of moving according to these constant velocity dynamics. Okay. If we're moving to regions of higher density, then V transpose log pi would be positive. So this minus it would be negative, and the overall rate would be 0. So in that case, there would be no events. We just keep on moving. But if we're moving to regions of lower density, there'd be some sort of positive rate at which an event would occur. Okay. And then the final thing is what happens when there is an event, and at an event, the position theta remains unchanged, but the velocity changes, and the velocity is just reflected. And essentially what you can think of is that if you think about the gradient of log pi at the position theta where the event occurs, all that happens is the velocity component in the direction of the gradient is just flipped. Okay. And this is just showing what a realization of the bouncy particle sampler would look like for some sort of target distribution, two-dimensional target distribution, whose contours are given by the gray lines. And in this situation, we sort of started the process at the origin with a velocity which is sort of moving up and to the right. And you can sort of see it has these sort of constant velocity dynamics, so it moves in a straight line until in regions where it's moving to regions of lower density, there's some chance of an event happening, at which point the velocity sort of flips and it then moves in a different direction. So the sort of path would have been something like this. Okay, and so the realization of the process is this sort of continuous path given by the black line. One of the nice things about these processes is that whilst a realization of the process is sort of is the continuous path, you actually can sort of reconstruct the path just by knowing when and what happens at the events. Okay, so essentially, in order to reconstruct the black line, all you would need to know is what the red dots are, and essentially you would reconstruct it just by joining the dots together. It's a little bit of an aside, but if you were to implement the bouncy particle sampler, as well as the three events, the dynamics I described, you would also tend to want to introduce what are called refresh events, which are just sort of random times at which you just sample a new velocity for your process. And the reason for this is that, in some sense, the dynamics of the bouncy particle sampler are sort of a bit too deterministic, which means that in some examples, the bouncy particle sampler can actually be sort of reducible. So that depending on how you start it, if you're sampling from a sort of Gaussian density, there can be regions of theta space that you can never reach. Okay.
Even though you can put the randomness also into the law with which you rebound, if you want to.
Yeah. So you do. So in order to avoid that, you would need to introduce some extra randomness. Well, possibly the most common is you just have these random times where you just simulate a new velocity. And even in situations where you wouldn't actually have the process being reducible, you can get some very weird behavior if you don't have these refresh events, as seen here, where here's some sort of target, the sort of heat map for some target, and you sort of, if you just run the bouncy particle sampler without refresh, you get this relatively slow sort of mixing where it just sort of loops round and round. Whereas with the refresh event, it mixes much better. So there are many sort of nice properties of the bouncy particle sampler in terms of using them for sort of Monte Carlo sampling from pi. But there's one sort of big difficulty is in that, in general, they're actually very difficult to implement. Okay, and so I wanted to spend a little bit of time explaining why this was. So the only difficulty in sort of simulating a realization of the bouncy particle sampler or these other PDMP samplers is simulating when the events occur. So how would you go about trying to simulate when the events occur? So the event rate depends on the current state of the process. But what you know is that up until, given the current state of the process, up until the next event, you know what the state would be because of the deterministic dynamics. Okay, so what that means is that you can sort of, you can actually construct a rate for the next event as a function of the time to the next event, just by taking the rate as a function of the state and plugging in what the state would be at time t in the future if there hasn't already been an event. Okay, and that's what we've sort of written here. So theta t vt is the state of the process at time t in the future. If there's been no event, that would define what the rate of an event occurring at that time point. Okay, and I've called this lambda tilde of t. Okay, so just viewing this as a function of t. So in order to simulate when the next event for our bouncy particle sampler occurs, what we'd need to do is simulate what's the time of the first event in a sort of Poisson process, a time inhomogeneous Poisson process with rate given by this lambda tilde. Okay. And so that's just what I've sort of said there. Now the problem that you have is that unless lambda tilde is of a particular particularly simple form, you can't actually simulate that time sort of analytically. Okay, so if lambda tilde of t was a constant, then it would be easy to simulate when the first event occurs. It also turns out to be straightforward if lambda tilde is linear or piecewise linear. In that case, you can sort of analytically or directly simulate when the next event would occur. But for more general, more complicated rate functions, lambda tilde, it's difficult, or it's impossible to sort of directly simulate when the first event in this process would occur. Okay. So there is a way around that, and that's to use something called thinning. And the idea of thinning is that what we can do is we could try and come up with an upper bound on the event rate, okay, chosen so that the upper bounded event rate is of a relatively simple form, such as constant or piecewise linear. Then we could simulate possible events using this upper bounding rate. Okay, that would give us too many events, but we can then introduce a sort of accept reject step to sort of remove some of those events, so we just end up events which occur with the correct rate. Okay, and so if we have an upper bounding rate which is given by lambda plus, what we would do is we would simulate events from a Poisson process with this event rate, and each time we simulate event, we just have to decide whether it would have occurred with the event rate that we want, lambda tilde, and to do that we would just accept the event as occurring with a probability which is the true rate, lambda tilde, divided by the sort of upper bounding rate, lambda plus. So if we can do this, if we can come up with an upper bounding rate, lambda plus, then the algorithm then would actually be quite easy to implement. Okay, and I'll just explain it in sort of pictures. So we'd start off our algorithm with an initial state, so initial value of theta, and not shown on this would be an initial velocity. Okay, given that, we could then calculate what the true event rate lambda tilde is, so that the rate as a function of time to the next event, and we would come up with our upper bound, sort of lambda plus, and then we just simulate the first event in a time inhomogeneous Poisson process with rate lambda plus. Okay. Once we do that, we then just propagate the continuous time dynamics for that period of time, and then we just need to decide whether or not that is an event in our bouncy particle sampler. So we'd look at the state at this time, we'd calculate what the true rate is at that time, and have an accept the event with the true rate divided by the bounding rate. Okay. If we don't accept the event, then the velocity is unchanged, and we just repeat. So we just potentially recalculate an upper bounding rate, simulate the next time using that upper bounding rate, move forward to that time, calculate the true rate at the new state I have, and again do an accept reject step. Okay, and if we do accept, then an event has occurred in our bouncy particle sampler, so we would just reflect the velocity of our process in the sort of gradient of log pi at that point. Okay, and then we just sort of repeat. Okay. So in some sense, doing this is sort of quite easy to do, contingent on the fact that we can come up with a good upper bounding rate. Okay, and the problem that you get is that it's actually very difficult in general to come up with good bounds on the rates at which events occur. Okay, and if you have a bound, so a bound which is a lot higher than the true rate, what that means is that so you'll still be simulating exactly the same process if you have a bad bound, a bound which is much too high. The problem that you get is that it just becomes computationally very inefficient, because you're just simulating lots of these potential events which don't occur. Before I go on to talk about the sort of algorithm we've been investigating, there's another important sort of nice property of these PDMPs which we're going to sort of utilize, and that is that they give a sort of principled way of using sort of subsampling ideas. Okay. So what do I mean by this? So this is particularly relevant in situations where what we're trying to sample from is the posterior distribution. So pi of theta is a posterior distribution, which in general, so will be proportional to the likelihood, which I've denoted by f naught of theta. Sorry, so the prior, which I've denoted by f naught of theta, times the likelihood. And if we have capital N observations, often the likelihood will just be a product over likelihoods associated with each of the N observations. So if we then think about what's happening with the bouncy particle sampler, when we're implementing the bouncy particle sampler with thinning, at each time when we're deciding whether to accept or reject an event, we need to calculate what the true rate of an event is, and that depends on the grad of log pi. Okay, so that means that in order to calculate the true event rate, we'd need to calculate grad of log pi, which in this situation, log pi, so pi has this product over the data points, log pi would then give us a sum over the data points, and if capital N is large, the cost of then calculating the gradient of log pi could potentially be quite high, and certainly would be the computational cost of calculating grad log pi would be proportional to the number of data points, capital N. Okay. So there's been quite a lot of work in sort of Bayesian computational stats more generally of trying to sort of reduce the per iteration sort of computational cost of algorithms by replacing, say, the true gradient of the log posterior by an unbiased estimator of the gradient. Okay, and that can be done quite easily because the gradient of log pi is just a sum. So one way of getting an unbiased estimate of the gradient is just, well, what I've sort of described sort of here. Okay, so the true gradient is the grad of log of the prior plus the sum of the grad of the log of each of the likelihood terms. But we can get an unbiased estimate of that just by replacing the sum over the data points, just by choosing one of the data points at random and using n times the gradient for the corresponding log likelihood term. Okay. And if we think of this estimator and we choose I sort of independently or sort of uniformly from 1 to n, then this estimator would be an unbiased estimator of the true gradient of log pi. And so the idea of these sort of subsampling approaches is would it be possible to sort of implement our algorithm where we replace the sort of costly step of calculating the true gradient of log pi with the much cheaper cost of calculating this unbiased estimator of log pi?
Excuse me, if you implement it just like that, then it's a wrong algorithm, right?
If I
mean, just you take it like this, and instead of computing the gradient, you can just take one of the i's and compute this estimator. Then you run it, it's wrong, right?
Well, it depends how you implement that. So if I, okay, so the way you can implement it where it is correct in some sense is the following. So, so previously we had this idea of using sort of thinning. So we had this upper bounding rate. We simulated potential events with that upper bounding rate, and then for each of those we would make a decision whether to accept or reject it. Okay. If you can come up with an upper bounding rate which holds sort of uniformly, regardless of which of the estimates of the gradient you use, okay? And then you implemented the sort of previous algorithm, but at each time point when you would, at each iteration when you were deciding whether to accept or reject, you just, rather than using the true gradient to get the true rate, you just used, you just simulated one data point, got the unbiased, got the estimate of the gradient, and used the corresponding rate. Then that algorithm would be correct in the sense that it would still involve simulating a PDMP whose theta marginal is pi of theta. Okay. So just a few comments on this. I haven't planned to go into all the details, but essentially if you do this, you're actually no longer simulating the bouncy particle sampler that I described before. You're simulating another piecewise deterministic process, okay? But the sort of, the perhaps rather surprising thing is that whilst you're simulating a different piecewise deterministic process, it still would have pi of theta as its theta marginal, okay? The process that you're simulating actually has higher rates at which events occur. Okay, so you can actually work out what the event at which, the rate at which an event is occurring, and it turns out that it's of this form here. Okay, the true bouncy particle sampler would have a rate which is the maximum of 0 and the average of these terms. Okay, just because the gradient, the average of the gradients is the average of our estimates of the gradients is the true gradient because of the unbiasedness property. The actual rate at which you're simulating events with this with this algorithm, which uses subsampling, is greater because it's just the average of the maximum of 0 and the average of 0 and minus v times the estimate of the gradient. Okay, so you potentially would have cancelling out if you sort of move the sum within the maximization, which you don't get here. Okay, so you're simulating a process with a higher rate, but it turns out that the invariance of pi of theta for the sort of PDMP sampler actually is determined by the rates through essentially the sort of difference in the rates, essentially sort of the rate of changing the velocity v to something new compared to changing the rate at which you would do the reverse sort of transitions. Okay, and it turns out that although you're using a different rate, that difference is still the same as with the bouncy particle sampler. And it's that sort of property which means that the stationary distribution, or the theta component of the stationary distribution of the process is the same as for the true bouncy particle sampler. So this is nice in the sense that you can use subsampling and still have an algorithm with samples from the true target, the true posterior pi of theta. And the computational benefit is that the computational cost per iteration is now of sort of order 1 rather than order n, because in order to decide whether to accept or reject a possible event, you're just using this sort of cheap estimate of the gradient rather than having to calculate the true gradient. Okay. The disadvantages.
Yep. Can I make a comment? I mean, it's just very interesting. So just to connect what other people have done is that if you take the VT to be a slice sampler, right? I mean, if all the V's are 0 except of 1 or 2 or 3 or 4, then also you don't have to compute the whole gradient. Then you only have to compute some coordinates. That's what we have done for 10 years. That's how we avoid computing the gradient. Right? If you just take, you say V is equal to 0 or just for pi, then you only have to compute the gradient of log pi of I.
Now, Bernard, the analogies with when you have a single particle moving with long-range interactions.
No,
And then
I'm not talking about
really
long.
subsampling in that context. Because you
Sometimes
sample an event for each of these
So the
parts.
key is to avoid computing the gradient, I mean, of the whole system.
Yeah, but the difference here is that I here is over data as opposed to component of theta. So I think the trick is similar to what you're describing, but it's a little bit different in this situation.
It is different. Sum over the data, sum over the two particle interactions. That's not the analogy.
Just quickly related to the previous comment, if you first sampled I and then had an upper bound on GI for this chosen I, then the algorithm would be incorrect. Yeah.
So the disadvantage of doing this, so there are two disadvantages. One is that the process that you simulate has a higher rate at which events occur, and that adversely affects the mixing of the algorithm. And what that means is that if you could implement this algorithm, you can sort of show that you only really get sort of noticeable gains if you use good estimates or low variance estimates of the gradient. So the naive estimates of the gradient I had on the previous slide don't actually give you gains in sort of practice. You would need to use sort of cleverer estimates using things like control variance. Okay, but the biggest drawback with this is that it's even harder to implement than the sort of standard BPS, because you still have to find this sort of upper bound on the rate, but now it's a much harder problem because you need to get this bound which is sort of uniform over the rate that you would get regardless of which data point or which estimate of the gradient you have. So what we've been working on is a way to get over the sort of difficulty of simulating, say, something like the bounded particle sampler with subsampling just by simulating an approximation to it. Okay? And what you can think of is this is sort of similar to what you have in, say, sort of with the Langevin diffusion. In general, it's impossible to simulate exactly the Langevin diffusion, but what you can do is you could just simulate an Euler discretization to the Langevin diffusion, and that gives you the sort of Euler algorithm. Okay, and so we're going to do something similar. So essentially, we're going to do things a bit like sort of Euler-like discretizations of the bounded particle sampler with subsampling. Okay, and as I mentioned, the idea of just of simulating approximations to PDMPs actually originated in earlier work by Andrea, Joris, and others. And they have quite a lot of nice theory sort of studying the properties of these methods. So the basic idea of doing this is that we're going to, if you think about Euler discretization, we're going to sort of discretize time into intervals of length delta, and then we're sort of going to have sort of relatively simple dynamics over each of these intervals. Okay, and the way we're going to do this for the bounded particle sampler with subsampling is we're going to decide which data point we're going to use for this interval a priori. Okay, and then we're going to not worry about how the rate changes over the interval. We're just going to look at what the instantaneous rate of an event is given our current state and this estimate of the gradient, and we're just going to fix that rate over the period of the time interval. And so this gives you this sort of algorithm. Okay, so if we want to simulate the process over the next time interval of length delta, we simulate a data point. We then look at the rate that we get using that data point's estimate of the gradient and our current state. We then simulate the time for the next event with this sort of constant rate, so that just involves simulating an exponential random variable. And then one of two things could happen: either the time until the next event will be bigger than delta, in which case there'll be no event in our interval of length delta, and we just propagate the deterministic dynamics to the end of the interval, or the time to the next event will be less than delta, in which case we just simulate the dynamics given that event time. So we simulate the deterministic dynamics for time tau. We then calculate the gradient of log pi, or estimate of the gradient for log pi using data point I at that position, and we do the sort of reflection, and then we just simulate the deterministic dynamics for the rest of the interval. And so this is just in pictures what would happen. So we'd start off with a position and a sort of velocity. We sample a data point. Given that position and velocity and our estimate of the gradient, we would calculate an event rate. We would then simulate an exponential random variable with that rate. If the value of that exponential random, the realization of that exponential random variable was greater than delta, we would just propagate the deterministic dynamics over time interval length delta, and we would just repeat. Okay, so sample a data point, calculate the rate, simulate the time to the next event by simulating an exponential random variable. If there's no event, we just simulate the deterministic dynamics to the end of that interval. And then if there is an event, we would then just simulate the dynamics up until that event time, work out what the reflection would be, update the velocity, and then simulate the rest of the dynamics over the rest of the interval. Okay, and just keep on doing that. Okay. So that's the idea. So at least in terms of being able to implement the algorithm, it is now sort of trivial to do. I mean, the difficulty in simulating these things is simulating when the events occur, and now we've reduced that just to simulating an exponential random variable. Okay. The question then is, what can we say? We're no longer simulating the correct process, so what can we say about the sort of error? Okay. And so, I mean, this is discussed a bit in Andrea and Joris's paper, but here's how we think about it. So the approximation error with the approximation that we have in implementing this algorithm is just in terms of the distribution of the time until the next event, and we're sort of simulating that from the wrong distribution. Okay, so we're going to sort of think about what the error in sort of simulating the time to the next event is. Okay, and the way we're simulating the time to the next event is that we're sort of simulating a data point, where then for each data point there'll be an associated sort of constant. So over an interval of length delta, for each data point there'll be a fixed event rate, which I've denoted on this slide by lambda I. Okay. So we're sort of choosing essentially a random one of these lambda i's, and then we're simulating events with that fixed event rate lambda I. Okay. However, you can sort of consider that process of simulating events by simulating a lambda I and then simulating events with that constant lambda I as equivalent to sort of simulating events with a time-varying event rate, which I've denoted by lambda hat t. Okay, so this is just sort of marginalizing out over the choice of which data point we've chosen. Okay, and so lambda hat t is the sort of effective rate of an event at time t within our interval of length delta. Okay, and so what this rate is it's a measure of what's the probability of an event occurring in sort of between t and t plus delta t given that no event has occurred up to time t. Okay? And so it's quite easy to sort of calculate what that is, and it's essentially a sort of weighted average of the fixed event rates lambda I, where you essentially are weighting each of the event rates by the sort of probability that if you'd chosen that event rate, there would not have been an event at time t. Okay, so the effective rate at which you're simulating events is of this form. Okay. And then once you have this expression, you can sort of see a little bit of what's happening and what the approximation is. Okay, so at t is equal to 0, the event rate that you're using is the true event rate that you want to use. Okay, in that case, lambda hat t is just an unweighted average of all the lambda i's, and by this unbiasedness property, that corresponds to the true event rate that you'd want to be simulating events at. Okay, but as t increases, for t strictly greater than 0, this will be the wrong event rate, and it'll be wrong for two reasons. Okay, the first reason is that it ignores any changes in the sort of event rates associated with each of the data points over the time interval. Okay, the fact that we're just fixing the rate associated with each of the data points is one source of error. But the bigger source of error is this second point here, which says that if you think about what's happening as t gets larger, rather than having an unweighted average of all the lambda i's, you've now got a weighted average of the lambda i's, such that you're giving more weight to lambda i's which are smaller, okay, and less weight to lambda i's which are bigger. Okay, so that's going to introduce an error, and in particular, it's going to be an error which tends to sort of lead to underestimation of you're using an event rate which is smaller than the event rate that you want to do for t is greater than 0. Okay. And this is just a sort of a figure sort of numerically showing the sort of errors that you get. So for this plot, all I did was I just took an implementation of the bouncy particle sampler with subsampling, fixed an initial state for the process, and looked at the distribution of the time to the first event in the process, and sort of numerically calculated that in the sort of grey line for the sort of true BPS with subsampling, and with the red line, the distribution that you're simulating from if you use this sort of approximation to it, okay? And the three different plots just correspond to different values of delta. And so what you have is that you sort of see, if you just focus on the left-hand plot, you sort of see this problem that comes through this sort of underestimate of the true event due to the fact that you're just fixing a single data point and using the rate for that data point over an interval length delta. Okay, so you tend to have initially the rate's correct, so they sort of match at time 0, but then as you go over the interval length delta, you're using too small a rate. Okay, once you get to the end of your interval length delta, you sort of reset things, so now you're using the correct rate. However, you've had too few events so far, so that leads to this sort of jump above the true density, and then you sort of get a similar pattern going forward. But what you can show is that the sort of error in the approximation of the, between the approximation error between the sort of rate you want to be simulating and the rate that you are simulating is sort of linear in the discretization error sort of delta, and then using the sort of results from the Tazzi et al, that then gives you essentially the sort of bouncy particle sampler algorithm that you're simulating will also have an error which is linear in delta. We've done some sort of some simulations implementing this. I don't have any results here. There are some results in this sort of archive preprint. I don't have any results because they're not particularly exciting. So the natural thing to sort of compare this algorithm with is other MCMs or other algorithms based on approximations of sort of MCMC that use sort of stochastic gradients, such as stochastic gradient Langevin dynamics. And it turns out in a lot of the simulations we did, this algorithm and stochastic gradient Langevin dynamics basically do very similarly, both in terms of the level of accuracy and also in terms of the sort of the types of errors they make. So both of them have this property that they tend to lead you to sampling from a density which places more weight in the tails than the true target density does. Okay. The one benefit we seem to see over stochastic gradient Langevin dynamics is that because of the sort of constant velocity dynamics that we're using with these PDMPs, they tend to be more robust in situations where potentially we're using sort of too large a step size, or the variance of the gradients is very large. Okay, if you use these Langevin dynamics and you just get a very bad estimate of the gradient, that can completely mess up your sort of sampler, whereas the impact it has on these sort of PDMP samplers is much less. But to finish with, I want to talk about a way of improving on the algorithms that I've just said, based upon the idea of trying to sort of correct some of the error that we're making when we're, the error in the event rate that we're making when we were implementing the previous algorithm. Okay, so what I showed with the algorithm I introduced before is that so within each time interval length delta, the instantaneous rate is correct at time 0, but tends to become too small for time t is greater than 0. Okay, and the error for t greater than 0 comes from two things. One is that the true rates are varying over time, and one comes from this sort of downward bias due to how we're doing this sort of subsampling. Okay. Now, in terms of the downward bias that comes from the sort of how we're doing this, the subsampling, or the fact that we're just choosing a single data point and fixing it for the interval length delta, you can then sort of look to see what the error is. Okay, and to first order, the error is sort of linear in time, and the coefficient is equal to the sort of variance of the rates of the lambda i's that I had. Okay, so this suggests this thing is maybe we could try and introduce or inflate the rate at which we're simulating events by a sort of linear function of t to sort of compensate for this effect. Okay, and this was an idea that I think Gareth first had, and it turns out that you can actually do it in a very sort of simple way, and all it requires you to do is, rather than simulating one data point for each interval of length delta, you now need to simulate 2 data points for each interval of length delta. Okay, so this is what you do. So you sample 2 data points I and j independently and uniformly from 1 to n. So just choose 2 data points. Okay, these will give you your estimates of the gradient, and then from that you can calculate the corresponding rates associated with these gradients and the current position for those lambda I and lambda j. And then what we're going to do is we're going to consider simulating an event where if there is an event, we're going to use the gradient associated with data point I to do the sort of reflection. Okay, and there's a slight mistake here. So what we also need to do, if we're trying to get a better approximation to the true rate at which events are occurring, we need to also take account of the fact that the true rates are varying over time. And so that means that we also need to, the data point I, we need to get an estimate of how the gradient, how the rate associated with data point I would be changing over time. so the derivative of the rate at time 0. And then what you do is you just need to simulate an event with this rate here. So this has the rate, the instantaneous rate associated with data point I as before, but then you add on a function which is linear in t. The first term is trying to deal with the fact that the true rate associated with data point I is varying over time. And the second term here is to try and inflate the rate to take account of the fact that you were sort of fixing the sort of data point you have for that interval. Okay. And what you can do is you can then, it's relatively straightforward to show that if you use this rate, then as before, the rate at which events occur instantaneous at time 0 is the true rate, but you can also show that the derivative of the rate that you're using at time 0 is equal to the derivative of the rate that you'd want to use. Okay, and therefore under some assumptions that means that the overall error in the rate that you have over an interval length delta would now be of order delta squared rather than order delta. And this is just trying to show this sort of numerically. So this is just going back to the plot I had previously, where we had the true distribution of the time to the next event in grey, and the distribution we're simulating from with the sort of Euler approximation in red for different discretization errors. And now I've just added on, it's a little bit hard to see, a curve in blue, which is the distribution of the time if you use this sort of improved sort of second order method. Okay, and you can sort of see it, you know, at least in this example, it does give you a much better sort of approximation. And if you look at the sort of overall error in the rates or in the distributions you're sampling from, you can actually numerically observe that the errors are going down with the square of the discretization distance rather than just linearly with the discretization delta. And just in terms of how that impacts the efficiency of the sort of bouncy particle sampler that you simulate, here's just one example result where we just tried things out on a sort of toy, so linear regression model, and just looked at how these different implementations of the sort of bouncy, approximate implementations of the bouncy particle sampler with subsampling works as a function of the number of covariates, so as a function of the dimension of the posterior. Okay, and essentially this is just some measure of the error of the distribution that you're sampling from, so some measure of the error between pi of theta, the true posterior, and the distribution that your algorithm is sampling from. And essentially the sort of top line is the error you get if you use the sort of first order method, the sort of the first method I described, and then the other two lines correspond to two different implementations of this improved method that I've just mentioned. So the middle of the two lines is the algorithm that I had on a couple of slides ago, and there is a way, at least, of not improving the rate, but at least in practice, seemingly to improve the sort of numerical performance of the algorithm using some sort of ideas akin to sort of Rayet-Blackwellization. Okay, and just using the fact that here I had a rate which is really based primarily on using the rate for data point I, but if I've sampled I and J, I could also think about doing it using the equivalent thing where I just swap over I and J and use it based on the centered around the rate for data point J. And if you do that, then that seems to numerically improve the performance of the algorithm. Okay. So I'm pretty much out of time, so here's just a sort of summary. Yeah, I guess the main things are that, you know, these what we call stochastic gradient PDMP, so these approximate implementations of PDMPs like this bouncy particle sampler with subsampler are now trivial to implement. And with the sort of trick that I mentioned at the end, I guess the main thing is that there are ways of doing this with an approximation error which is now sort of quadratic in the discretization size rather than just linear. We're still at a very early stage of actually sort of investigating in practice how they work on sort of challenging problems. So I'll stop there and just leave a few references, and thanks for listening.
Thank you. One comment, so are you, maybe just to be aware of recent work of Andrea and Pierre of using higher order approximation or the splitting methods to have less approximations of these PDMPs, which I think would be interesting in this method. And the question is, so I guess it would be interesting to also study how does it scale with n, so the size of the data set. That's something that you...
Yeah, so the scaling with n, so what sort of matters is the sort of variance in the rates for different, as you sample different data points. So the scaling with n will then depend a lot on what's happening in terms of that variance, which in turn depends on what estimator you're using for the gradient. But yeah, I mean, I think that we haven't really looked at that.
Maybe like order n or order n to the half or so could be maybe made in a general.
Yeah, yeah. So I mean, it's all gonna. So I think you can sort of. There would be results which would sort of relate. Well, at least in the sort of first order method, which relate the error to the variance of your gradient, and then that's the thing which would depend on n and how you estimate it, and in some cases, because of the sort of concentration, if you use control variance, the variance of your gradients can get better as n gets larger, which can lead to sort of things working better for larger n. If you just, my guess is if you just use the very naive gradient estimator, yeah, things wouldn't get better with n.
I had a somewhat related question. I mean, I have in mind that in SGLD, you can do mini-batching, and in that case, the error is proportional to n squared over m, where m would be the size of the mini-batch. And you derive that by writing some effective equation. I was wondering whether it would be possible to do the same here. So instead of having just GI with one data point, you have n data points, and whether you could benefit from there by reducing a bit the error, and maybe also highlighting the first term in this effective equation, which would help you unbias maybe.
Yeah, so you can use mini batches. If using a mini batch of m, the improvement you get is less than sort of a factor of m. So if you view that the dominant computational cost was calculating, accessing the data points and calculating the gradients, I don't think there's any advantage of using m greater than 1 or 2 for the two algorithms. In practice, that's not going to be the case because there is additional overheads and so on, in which case using a larger mini batch size would help. But largely, particularly for small m, it probably in the things we've looked at empirically, it doesn't make much difference because doubling m probably improves the performance by a factor of 2, but doubles the computational cost by a factor of 2, so it also cancels out.
I guess it depends a bit on the variability of the GIs and the actual value of n. I mean, if it's like 1 million, maybe you would want a little bit of mini batching. If it's only a few hundreds, maybe it's less important.
Yes, but I think what you can do, so rather than, you could use, say, a given delta with m is 100, or you could use m is 1 with delta over 100. I think using m is 1 with delta over 100 would be slightly better.
So
So we are a bit late, so I think we can stop here with the questions and call again.